Alright, hi. Welcome to the first chapter of the dynamics series, and in these few chapters I'm going to be covering the entire chapter on dynamics. Right, this chapter basically is talking about forces, is talking about Newton's third law, is one of the most basic and fundamental chapters, especially for O-level physics. Right, this chapter, the reason why it's so important is because it's linked so closely to the other chapters. All chapters will always be built upon forces. So this is going to be the first chapter that you learn in Sec 3. Right, I know technically the first chapter is physical quantities, but this is basically the first real chapter that you're going to learn. So in this video, I've broken this chapter up into a few different parts. We're going to cover mass and weight, resultant force, vector diagrams, Newton's third law, all the different aspects of this course, so that by the end of these few videos, you'll pretty much be a master of dynamics. Right, you're going to be covering every single part of dynamics. So I really make sure that by the end of these few videos, you'll become very, very strong at dynamics. Right, so let's start with covering the first part, which is mass and weight. And also throughout these few videos, there's going to be few examples and exercises for you to try yourself. So make sure to pause the video and actually try the examples yourself, right? Because we know that for physics, it's all about practice. So now let's talk about mass and weight. Basically, what is weight? Weight is basically the downward force of gravity pulling you down, right? So example, if you stand on Earth, the force of gravity that pulls you down towards the ground, that's called the weight. Every single object on Earth has a weight of its own. You can see over here, this stone is being pulled downwards, and this force is called the weight. Now, in order to have the weight, you have to be inside the gravitational field of an object, right? So this one is the Earth, and this one is the gravitational field of the Earth. And basically, any object that is inside the gravitational field of the Earth will experience a weight, right? So you need to be inside of the gravitational field. Right, one thing to note is that the further away from the planet, the weaker the gravitational field strength. So if an object is over here, the gravitational field strength is very strong. But if you go a bit further away, the gravitational field strength becomes a bit weaker. So the weight becomes a bit smaller when you go further away. Right, so the formula we know is W equals to mg. Weight equals to mass times gravitational field strength. So example, if this object is 5 kg and gravitational field strength is 10 newtons per kg, then the weight of this object is 5 times 10 equals to 50 newtons. Right, newtons is the SI unit for force. So just one very common number that you need to memorize is 10 newtons per kg. So on Earth, the gravitational field strength, we can take it to be 10 newtons per kg. Right, this one is just a number that you gotta memorize. Now, this 10 newtons per kg is also known as the acceleration of free fall. Now, this one is more of a kinematics concept, which is the next chapter. But yeah, just take note, G has two different meanings. Number one is the gravitational field strength. Number two is the acceleration of free fall. Right, so very quickly before we do some exercise, I want to talk about the difference between mass and weight. Right, because a lot of students always mess up. They think that it's the same thing, but it's different things. So mass is the amount of matter in an object. Right, how much matter is inside of you. For example, in this rock, there is 5 kg of mass inside the rock. But weight is the actual force that's acting on the object. Right, so the weight is the 50 newtons force that pulls the object down. So weight is a force, but mass is just a mass. It's just how much mass you have. As for all the practices in the video, feel free to pause the video and try the practice question yourself. Right, so assuming that you have done that already, let's go through the first question. Basically, the weight of a rock on Venus is less than the weight on Earth. Right, so the weight of the rock on Venus is less than the weight of rock on Earth. Now we can see over here that on Venus and Earth, it's still the same two rocks. Right, it's still the same rock being on Venus and Earth. So we can say that the mass of the rock must be the same, because mass is the amount of matter inside the rock. If it's the same rock, the mass will still be the same. But the difference is the force. Venus has a smaller gravitational field strength, and that's why the weight of Venus is smaller, right? The weight of the rock on Venus. So mass is always the same, even if you go to a different planet, but the gravitational field strength of Venus is smaller. So answer for this question is C. Right, so usually for these kind of questions, the main idea is that the mass of object doesn't change as long as it's the same object, but the weight can change depending on the gravitational field strength of the planet. Right, let's try this next practice over here. As usual, feel free to pause the video and try the question yourself first. Now over here, we have a mountaineer of a weight 700 newtons at the bottom of Mount Everest. Okay, so at the bottom of Mount Everest, the weight is 700 newtons. From this info, we can actually calculate the mass of the man, right? Because we know that W equals to mg. We know that at the bottom of the mountain, the G field strength is 9.81 newtons per kg, right? So we can take 700 equals to m times 9.81. So mass equals to 71 71.356 kg. Right, now we know that over here, when a man goes from the bottom to the top, it's still the same man, right? The mass is still the same at the top. So the mass at the top is still 71.356 kg, but the difference is that the gravitational field strength at the top is different. So the weight at the top, we take the same mass times the new gravitational field strength at the top equals to 699 newtons. Right, so we can see over here, the weight is different, but the mass is still the same. So answer for this question is A. Right, obviously this one, we round up the answer from 71.3 to 71.4. Also notice that the further up you go, the weaker the gravitational field strength. Right, at the bottom of the mountain, you are closer to Earth, so the gravitational field strength is stronger. But as you go further away from the Earth, the gravitational field strength becomes weaker. So that's the idea with gravitational field strength. Now, let's talk about some common types of forces that you're gonna encounter in your exam papers. Right, the first type, the most common type, is normal force. Basically, normal force is whenever an object is touching the ground, it will always experience a normal force. And the normal force is basically the ground pushing up onto the object, right? So one thing about this normal force is that it's always perpendicular to the surface. Means that this one is 90 degrees, right? If you have an object like this on a slope, the normal force is gonna be like this, right? It's always 90 degrees to the surface. So every single time an object is touching the floor, it will experience a normal force. Now, second thing is friction. Friction is basically an opposing force that acts in the opposite direction of the movement. So if you're moving to the right and you're touching the floor will exert a friction on the left, right? Basically, the floor will try to slow you down. So same thing, if you're moving to the left, then the floor will try to push you back to the right, right? So friction always tries to slow you down in the opposite direction. Air resistance is kind of the same thing, except that air resistance happens in air. So if you're falling downwards, then the air will try to push you upwards to slow you down. Similarly, in the other case, if you were actually flying upwards, then the air resistance will try to push you downwards. So air resistance, friction, both always acts in the opposite direction of the movement. Right, so just some factors affecting air resistance. The first one is speed. So if you move faster, you will have more air resistance. Second factor is surface area. If you have very small surface area, the air resistance is not so much, right? Compared to if you have a very, very big surface area, the air resistance is going to be bigger, right? Because there's kind of more space for the air to push you. So bigger surface area, more air resistance. Now the last type of force that you're going to encounter is tension, right? Tension is basically when an object is being pulled by a string, the string is going to pull the object with this force called tension, right? So these are pretty much the four main types of forces that you're going to encounter other than the weight lah. So weight, normal force, friction, air resistance, and tension, right? So that's the most basic parts of dynamics, and I'll see you in the next video where we'll talk about resultant force. Right, now let's talk about resultant force, and now we're going to learn the main part of this chapter, and this is going to be, it'll start to get a bit more challenging from now on lah. But let's try to keep it as simple as possible. What's the resultant force? It's the combination of all the different forces. So if you have a box over here, and let's say you have 5 newtons force to the right and a 2 newtons force to the left, the resultant force is going to be 3 newtons to the right? Because the 5 newtons force to the right is being partially cancelled out by the 2 newtons force to the left. So in total, if you were to combine these forces into a single force, it will just be 3 newtons, right? That's the resultant force. It's just the combination of all the forces, right? So the formula that we know is resultant force equals to mass times acceleration, right? Resultant force equals to mass times acceleration. So example, in this diagram, if I say that the mass of the object is 1 kg, I can find the acceleration of the object by using 3 equals to 1 times acceleration. Then acceleration of the object is 3 meters per second square, right? So this one's going to be the main formula for this chapter, RF equals to MA. So I won't go talk too much about this. Let's just do some practice first, and we're gonna learn more concepts along the way. Now, if you look at the first question, okay, as usual, feel free to pause the video, try the question yourself first. But the idea with these questions is that you always want to draw the forces as well as the resultant force. That's the trick to solve these kind of questions. So we have a van of mass 1500 kg. So this one is my van, and there's a force produced by the engine, right? So assuming that the van is traveling to the right, there is 1150 newtons force pushing the van towards the right. Now there is also a frictional force that is in the opposite direction, because remember that the frictional force is in the opposite direction to the movement, right? So if the van is moving to the right, means that the friction must be to the left. So our goal over here is to find what's the value of this frictional force. Now we know that over here there is a resultant force to the right, because the van is moving to the right, it's accelerating to the right. So we know that this force must actually be bigger than this force. So overall the resultant force must be to the right. Now using the mass and using the acceleration, you can calculate calculate the resultant force using RF equals to MA. So we can say that resultant force equals to 1500 times 0.60 equals to 900 newtons. Now here comes the very important part, right? It's about making your resultant force equation. Now what do I mean by resultant force equation? Just now in the example that we covered, we know that resultant force equals to this guy minus this guy. RF equals to 5 minus 2. How I know it's 5 minus 2 is because the resultant force, 5 is bigger than 2 lah. So it's 5 minus 2, that's my resultant force, right? So what's my resultant force equation in this question? I can say that resultant force equals to 1150 minus friction, right? Resultant force is to the right. It means that my 1150 is bigger than the frictional force. So resultant force equals to 1150 minus friction. Then the remaining is the resultant force. And that's really the key to solve these questions. You want to be able to form this equation over here, right? In the next few questions, I'm gonna be, keep repeating this, but the main idea is that you want to form your resultant force equation properly. So now we can say that 900 equals to 1150 minus friction, and solving this equation we get friction equals to 1150 minus 900 equals to 250 newtons, right? So answer for this question is A. Okay, so this is a very standard question on resultant force, and the two things I want you to take note is that always draw the free body diagram. We call this the free body diagram. Basically draw all the forces acting on the body and also make your resultant force equation. These are the two fundamental steps that you must have. Okay, now let's look at this question. This question is gonna be a bit more challenging, but I'm gonna introduce a new concept for this question, right? So first of all, I want you to draw the free body diagram acting on the elevator. So we have the elevator, mass is 500 kg, and it's traveling downwards with a constant acceleration. So first of all, I know that there's two forces. There is the weight and there is the tension, right? The tension is the cable pulling up the elevator. I know that there's these two forces, but the question is, what is the direction of my resultant force? Is my resultant force pointing upwards, or is my resultant force pointing downwards, right? And here's the concept that I want to introduce. Your resultant force is always in the same direction as the acceleration. So if your resultant force is to the right, means that you accelerate to the right. If your resultant force is to the left, it means that you accelerate to the left, right? I mean, it kind of makes sense lah. Like if you push something to the right, means that it will accelerate to the right. So we want to ask ourselves, what is the direction of the acceleration of the lift? We can see over here, the lift is traveling downwards and is also accelerating downwards. So the acceleration of the lift is downwards. So we can say that the resultant force is in the downwards direction, right? And this one is very important because why? This lets us make our resultant force equation. So now we can say that resultant force equals to weight minus tension. If the resultant force is downwards, it means that the weight must be bigger than the tension. So we can say that RF equals to weight minus tension, right? Whereas if you thought that the resultant force was upwards, you will get resultant force equals to tension minus weight, and that will be wrong. First of all, figure out what is the direction of your resultant force, right? So once you make this equation, you can quite easily solve the question. RF you can calculate using MA, which is 500 times 2.0 equals to 1000. So subbing into this equation, we will get 1000 equals to W equals to mg. So 500 times 10. Remember that on Earth, the gravitational field strength is always 10. 5000 minus T. So T equals to 4000 newtons, right? And that's our answer for this question. Right, so this question is really gonna test us on our fundamentals of forming the resultant force equation. So do try this question yourself first, but let's break down how to do this question together. Now, weight I think is quite straightforward. Weight is just W equals to mg equals to 860 times 10. Right, the weight is just 8600 newtons. Now, draw and label the forces acting on a helicopter. So I know that there's going to be the weight, right? The weight always acts downwards. There's going to be the weight. There is going to be an upthrust. So upthrust is the force pushing up the helicopter. We call this the upthrust. Obviously in the exam, you got to spell out the full thing so you don't minus marks. So we just spell out the full weight. There's also air resistance acting on the helicopter. So what direction is the air resistance acting in? We know that the helicopter is flying upwards, and air resistance always acts in the opposite direction. So if the helicopter is moving upwards, it means that the air resistance must be acting downwards, right? Pushing down the helicopter. So these are the three forces acting on the helicopter, right? So that's part B. Now, part C is the part that we have to really pay attention to. What is the upthrust on the helicopter? First of all, we want to ask ourselves, what is our resultant force equation, right? RF equals to 1. But before we even make our resultant force equation, we must understand what direction is the resultant force in. Is the resultant force upwards or downwards. Now, the helicopter is moving upwards, right? It's moving upwards, and he's also accelerating upwards. So it means that the direction of the acceleration is upwards, right? It's moving faster upwards. So if the acceleration is upwards, remember that resultant force is always in the same direction as the acceleration, means that resultant force must also be upwards. Okay, this is the key, because if you get resultant force downwards, you'll get this entire question wrong. So now that we know that resultant force is upwards, we know that the upthrust must be bigger than these two because the total force is upwards. So now we can say resultant force equals to upthrust minus weight minus air resistance. Right, resultant force equals to upthrust minus weight minus air resistance. And once we get this equation, it's very easy to solve the rest of the question. We can say that resultant force equals to MA 860 times 4.0, 3440 newtons. So now we can say 3440 newtons equals to upthrust minus weight minus air resistance. Right, we know air resistance is 400 newtons. So we can solve upthrust equals to 12440 newtons equals to 12400 newtons. Right, always round down to 3SF. Right, and that's how you solve these questions. So again, two important things to take note. Number one is be very clear on what's the direction of the resultant force. It's always in the same direction as the acceleration. And second thing is to, right, make sure that you form your resultant force equation properly. Now we're gonna do one more practice question over here, and this question is gonna be a bit more challenging, but it can be solved by drawing the forces in a way that is easy to understand. Right, so the first thing with this box with string questions, right, I like to use this idea that the same string has the same tension and the same acceleration, right? Meaning that both of these boxes, they are connected by the same string. So this tension over here, which pulls P to the right, must be equal to this tension over here that pulls Q to the left, right? Both tension must be the same because it's the same string. Second thing is both boxes must have the same acceleration. Cannot be one box accelerate faster than the other box, right? They are moving together, so they must have the same acceleration as well. Let's just call this acceleration to be A, and let's call this tension to be T. Now the first step in this question is to find what's the value of this acceleration. Now this one comes with a bit of practice, but you realize that you can take the entire P and Q to be one 6 kg object, right? So if you take the entire thing to just be a 6 kg object combined, the only force acting on this entire object is this 18 newtons force, right? Because these two forces, they will cancel out if you combine the entire thing. So now using RF equals to MA, we can say 18 equals to 6 times A, acceleration equals to 3 meters per second square. Right, so now we figure out that the acceleration of both of the boxes is 3 meters per second square. Now we want to make a resultant force equation for each of the boxes, right? Let's consider box P only. In box P, there's only one force acting on P, which is the tension. So the tension is the resultant force on P. So we can say that for P, RF equals to MA, tension equals to 4 times acceleration, which is 3 meters per second square. So tension equals to 12 newtons. And that's the answer for this question, right? It's 12 newtons. Now, just because I'm trying to teach you all the concept, let's try to make a resultant force equation for Q as well, right? On Q is a 2 kg block. There are two different forces acting on Q. Number one is the 18 newtons force, and number two is the tension. So the resultant force on Q is 18 minus tension, right? That's the resultant force on Q. So using RF equals to MA, we can say that MA equals to 18 minus tension. 2 times 3 equals to 18 minus tension. And if you solve this equation, you will also get tension equals to 12 newtons. So the idea is that you can kind of combine this whole thing and make a resultant force equation. You can make a resultant force equation for P alone. You can also make a resultant force equation for Q alone, right? You can kind of break it down into smaller parts to make your resultant force equation. Okay, so that's the section on resultant force, and in the next section we'll be talking about Newton's laws. Alright, now let's talk about Newton's laws, but before we talk about Newton's laws, let's go and try this question over here first. Right, so feel free to actually pause this video and try this question yourself, because I guarantee that most students will get this question wrong. Right, so this question, if you put D, that will be wrong. And this really brings us to the idea of Newton's first law, which basically says that we gotta take note of this word constant speed. Now, what does constant speed mean? Constant speed means that the speed is not changing, right? The speed is not changing. It means that the acceleration of the object is 0. If the speed is not changing, it means that it's not accelerating. That's the first thing. Now, we know that if resultant force equals to mass times acceleration, and the acceleration is 0, it means that the resultant force must also be 0 as well. right? So in other words, there is zero resultant force acting on the object over here because it moves at a constant speed. So whenever you see this word constant speed, you need to automatically link to the idea that the resultant force acting on the object is zero. Now here's the part that many students always get confused. If the resultant force is zero, why is the object still moving downwards, right? Why is it that the object can still move even if the resultant force is zero? Now here's the idea. Resultant force equals to zero means that the speed of the object doesn't change. So there are two different possibilities. If you were already staying still and the resultant force is zero, then you just continue staying still, right? That's the first possibility. The second possibility, if you were already moving and the resultant force is zero, it means that you will just continue moving at a constant speed. So resultant force zero doesn't always mean that you're gonna stay still. Sometimes it means that if you're already moving, you just continue with the constant speed. So yeah, in this question, we know that because the resultant force is zero, F1 must be equal to F2 and F3 must be equal to F4. So answer for this question is B. Okay, so always remember to link constant speed to this idea of resultant force equals to zero. Okay, so now we talk about Newton's laws. Newton's first law is basically what we talked about just now. An object at rest stays at rest and an object in motion stays in motion. So if there's no resultant force, right, an object at rest will just stay at rest. If you're already moving, you just keep on moving, right? That's basically Newton's first law. So an object always continue in its original motion. So if you're staying still, you'll stay still. If you're moving, you'll keep moving. Right, so now Newton's second law, this one is not so important, but basically Newton's second law says that the object will always accelerate in the direction of the resultant force. So if I push the object to the right, then it will accelerate to the right. Right, so these are the first two laws. The Newton's third law is going to be the most important law out of all these three, and we're going to cover Newton's third law in the next section. Now let's talk about action-reaction pairs, which is basically Newton's third law. This one is one of the most misunderstood concepts in the entire O-level physics, but I promise you that if you truly understand this concept, it's not that difficult and it'll put you ahead of so many students. So what's Newton's third law? Basically, Newton's third law says that for every action, there's an equal and opposite reaction. So if A pushes B, it means that B will push back onto A. So example over here, if I punch the wall is going to punch me. Sounds simple, but it's not that simple. So what I want you to focus on is what object is the forces acting on, right? Over here, when I punch the wall, this force is acting on the wall because I'm punching the wall, right? The wall is the one that experiences the force. When the wall punches back my hand feels pain. And that's because the force is acting on my hand. So it's very important to clearly identify what object is the forces acting on. This force is acting on the wall because I punched the wall, and this force is acting on my hand because the wall punches my hand. Now, what you notice about this is that these two forces are acting on two different objects. One is acting on the wall and one is acting on my hand. And that's one of the main criteria of action-reaction pairs. So let's first go through the few criteria. The first one is that the forces are equal in magnitude. So if this one is, 5 newtons, means that this one must also be 5 newtons. Right, second one is they are in opposite direction. One is to the right and one is to the left, right? So other cases can be upwards and downwards. They must be in opposite directions. And the last one, the third one, which is the most important one, is the forces must be acting on two different objects. One force over here is acting on the wall and one force over here is acting on my hand. Two different objects cannot be acting on the same object, as I'll show you later, right? And this last condition is not that important, but basically they must be the same type. So both contact forces, both gravitational forces, both electric forces, that kind of thing, right? But most important is these three criteria over here. Now let me ask you a question. Is the weight and normal force considered an action-reaction pair, right? Assuming they are the same magnitude, are they considered to be an action-reaction pair? Now think very carefully about this. Think about the conditions for action-reaction pair, right? Answer is no. They are not an action-reaction pair. And the reason is because even though they are the same magnitude, even though maybe it's 10 newtons, even though they are opposite in direction, both of these forces are acting on the same object, right? The weight is what? Weight is the earth pulling down the object. So the weight is acting on the object itself, right? The weight of this box is acting on the box. The normal force is the ground pushing up the box. So the normal force is also acting on the box, right? So because both forces are acting on the same object, it's not an action-reaction pair. Remember that action-reaction pair, one must be acting on the wall and on the hand. They must be acting on two different objects. So the question is, if the weight and the normal force are not an action-reaction pair, what is the action-reaction pairs of the weight and the normal force? Right, first let's try to define what exactly is the weight. The weight is basically the force of Earth on the box, right? Take note, what object is the force acting on? The force is acting on the box, right? That's why I say force of Earth on the box, because it's the Earth pulling down the box. The normal force of ground on box, right? Take note again, this force is acting on the box because the ground is pushing up the box, right? So both acting on the box cannot be action-reaction pair. So here's a pro tip for the action-reaction pair. It's always defined as force of something on something, right? You can basically describe any force as the force of something on something. And if you want to find the action-reaction pair, you can just swap these two words around, right? So over here, the force of the hand on the wall, the action-reaction pair, you just swap it around. So it will be the force of the wall on the hand. You can always find the action-reaction pair by swapping these two words around. So if I want to find the action-reaction pair of the weight, I can basically call this the force of box on earth. So basically what's going to happen is that the earth is going to pull the box down and the box is going to pull back up the earth, right? This force is acting on the earth. These two are the action-reaction pairs with each other, right? Now, obviously the earth is very heavy, so the earth is not gonna fly upwards. But yeah, these are the two action-reaction pairs, okay? Now, the action-reaction pair for the normal, we can also say is the force of the box on the ground, right? I'm just swapping these two words around. So this force is acting on the ground and basically is the box pushing down onto the ground, right? The force exerted by the box pushing down onto the ground. That's why this force is acting on the ground. So actually, these are the action-reaction pairs. These two are the action-reaction pairs, and these two are the action-reaction pairs. One very common misconception that I see students have is they think that these two forces, they are the same force. But actually, it's a bit different. This force is the weight of the box, right? It's acting on the box. It's the earth pulling down the box. But this force is the box pushing down the ground, right? So what's happening over here is that the earth is pulling down the box, and the box is pushing down the ground, right? Two different forces. So that's basically the idea of action-reaction pairs. Right, let's now start with some practice questions. Now over here, a player strikes a ball using a bat, exerting a force F on the ball. Right, so as usual, feel free to pause the video and try the question yourself first. But basically, over here is the bat, and over here is the ball, right? And over here, they are saying that this is the force of the bat acting on the ball, right? So the action-reaction pair, if you recall, we can just swap these two words around, right? So the action-reaction pair is the force of the ball on the bat, right? So answer for this question is B. So take note over here, this force is acting on the ball, then the ball is going to push back onto the bat. So this force is acting on the bat itself. Okay, quite straightforward for this one. Now, this next question is a bit more interesting. So the main idea with this question is that you always want to be very clear on what object is the force acting on, right? Over here, we only care about the forces acting on the man. We don't care about the forces acting on the box. We don't care about the forces acting on the ground. We only care about the forces acting on the man, right? So let's draw the action-reaction pairs. Over here, the man is kind of like kicking the ground to the right. So the force on the ground is to the right, right? The man is kicking the ground to the right. And we know that from action-reaction pair, the ground is going to exert a force in the opposite direction on the man. So this force is acting on the ground and this force is acting on the man. So if we were to look at the forces acting on the man's feet, it is to the left. Right, same thing over here. The man is pushing the box to the left. So because the man pushes the box to the left, it means that this is the force acting on the box. Right, the force on the box must be to the left. And by Newton's third law, the box is going to push the man to the right. So the force acting on the man is to the right. So answer for this question is D. Okay, so always make sure that you're clear on which object the forces acts on. All these forces are acting on the man. We don't care about these two forces because they're not acting on the man. Okay, this one is another very classic question, right? Over here, the wheel is traveling to the right. So first of all, you gotta understand that, okay, there's two ways to solve this question. The first thing is, if the wheel is traveling to the left, it means that the wheel must be rotating in this way, right? It must be rotating in the anti-clockwise direction. So if the wheel rotates in this direction, what you realize is that the wheel is going to sort of brush against the ground this way, right? The wheel is going to be brushing against the ground in the right direction. So the wheel is going to push the ground this way, which means that the force on the ground is to the right? Actually, let's just be a bit more specific. The force by the wheel acting on the ground is to the right. So by Newton's third law, we know that the ground is going to push back on the wheel. So over here, the force of the ground acting on the wheel must be to the left. And out of these two forces, which force do we care about? We only care about the forces acting on the wheel, right? So answer for this question is D. We don't care about the force that's acting on the ground. Now, that's the first way to solve this question. The second way to solve this question is a bit more, like, it's kind of dumb lah. But basically, if the car is traveling to the left, right, the wheel is part of the car. So if the car is traveling to the left, it means that the force on the wheel must also be to the left. So answer is just D. Yeah, so basically there's two ways to solve this question, but it's important you to understand the first method, right? Identify which body the forces is acting on. Okay, now this question is going to require a bit of knowledge from the next chapter, which is kinematics. Okay, basically the first question, part A, Answer is 2.4, right? So with this info, you can solve the rest of the questions just using dynamics knowledge. So determine the force acting on the man by the ground. So first of all, we must be very clear. What object is this force acting on? We only care about the force acting on the man, right? So actually in this diagram, there's the weight of the man and there's the normal reaction force. And you realize that they're actually asking for the normal reaction force, right? Because the force on the man by the ground is the ground pushing up onto the man, which is the normal reaction force. So they're basically asking for this force over here. Now you want to ask yourself, what's the direction of the resultant force? Is the resultant force acting downwards or upwards? Over here we see that the man is actually jumping upwards. So the man is actually accelerating upwards. Means that the resultant force acting on the man must be upwards, right? Remember just now that the resultant force is always in the same direction as the acceleration. So if resultant force is upwards, now we can make an equation: resultant force equals to normal minus weight, right? And taking RF equals to MA, we can sub in 168 equals to normal minus weight equals to mg, normal force equals to 868 newtons. So that's the answer for this question. Okay, so the force in B, which is the normal force, and the weight is not an action-reaction pair. This one we covered just now. Normal and weight are not an action-reaction pair. So what is the force that is action-reaction pair with the normal, right? Remember that normal is the force of ground acting on the man. And to find the action-reaction pair, we just want to swap these two words around, right? So the action-reaction pair will be the force of man on the ground. Okay, so just to be safe, you also want to say that it is equal in magnitude. It acts downwards because we're talking about this force over here acting on the ground, and also it acts on the ground. Okay, so that's the idea with action-reaction pairs. Okay, so now we're going to talk about inertia. Inertia is going to be kind of a short section, but the main idea with inertia is the tendency of an object to resist changes in the motion, right? But obviously if you read this, it's a bit hard to understand. Basically the idea with inertia is that if you are not moving in the first place, you want to stay still, right? If you're not moving, you want to continue not moving. If you were already moving, then you want to keep moving. So example over here, if you have a man inside a car, right? Both the man and the car are moving, but if the car suddenly stops, what's going to happen is that the man jerks forward. Why does the man jerk forward? Is because when the car stops, the man wants to continue moving forward, right? So the car is going to stop, but the man wants to continue in its original motion, so it's going to fly forward. Okay, so basically inertia is an object that is staying still wants to stay still, an object that's moving wants to keep moving. Now imagine you have two different stones over here and you want to kick the stone, right? Obviously the small stone is going to be easier to kick compared to the bigger stone. The bigger stone you need to like kick very hard, then it'll move a bit, right? Why does the bigger stone need more force to kick? It's because inertia only depends on mass. If you have a bigger mass, it means that you have more inertia. That's why this guy has a bigger tendency to just keep staying still compared to this guy who, you know, very easily he can fly away already because he got less inertia, right? So the thing about inertia is that it only depends on the mass of the object. Now let's talk about vector diagrams, right? This one is pretty much one of the hardest parts in this chapter, and a lot of students always get this part wrong. And okay, I know, I say like every part, most students get it wrong, but this one really, a lot of students get this wrong. So in this video, I'm gonna be trying to break down vector diagrams in the simplest way possible for you, right? So basically, like what's the idea behind vector diagrams? If I have two different forces over here, very easily I can find the resultant force, right? The resultant force is just 3 newtons to the right. Now the problem is, what if I have two forces like this? How do I find the resultant of these two forces? And that's where vector diagrams come into play. So you want to add these two forces together using the tip to tail method over here, right? This one is a very long list, but I'll just show you how to add it. So over here, if we have these two forces, how do we find the resultant of these two forces? The first thing I'm going to do is I'm going to take one of the forces like this. Next thing, I'm going to connect the second force to the end of the first force like a snake. This is called the tip to tail method. So I'm going to connect my second force to the end of this force like a snake, and once I've connected all the forces, I want to draw a line from the start all the way to the end, just like this. This one is my resultant force, right? And honestly, that's it. That's the entire thing. So you connect the forces like a snake, then you draw a line from the start to the end. Now take note that the resultant force is always pointing from the start to the end, so it's this way, right? It's not in the opposite way, okay? And the thing about this is that the order of the forces doesn't matter. So imagine if you decide to start with, you want to start with this force instead, right? Also can. You start with this force, then you connect the other force like a snake, then you draw a line from the start to the end. You can see that the resultant force is the same in both cases, right? So the order of the forces doesn't matter in this case, okay? So that's the basic method on how to add forces together using the tip to tail method. Let's try to do some practice over here. So pause the video, feel free to try this question yourself, and assuming you've done that already, let's find the resultant force of B. Over here, I have 3 different forces, 40 Newton, 60 Newton, and 80 newtons, right? So to find the resultant force of B, what I'm gonna do is I'm gonna take the forces, connect all the forces like a snake, and after I've connected all the forces, then I draw a line from the start to the end. This is my resultant force of B, right? Let's find the resultant force of A. So A, we have this force, we have this force, and we have this force. So to find the resultant of A, what I'm going to do is I'm going to connect all the forces like a snake, then I draw a line from the start to the end. This is my resultant force of A, right? And I'm going to do this for the rest of the options just to make sure that we are very clear on how to find the resultant force. So for C, it'll be like this. So it'll be connect the forces like a snake, and this is my resultant force of C. Right, for D, it'll be like this. I connect the forces like a snake, then I draw a line from the start to the end. That's my resultant force of D, right? So we can see over here, out of all these options, the one with the largest resultant force is option A over here. So answer for this question is A. Okay, so let's do another example over here. Let me show you a wrong answer first. For B over here, we have F1 and F2, right? So if I want to find the resultant of F1 and F2, what I'm going to do is I'm going to connect them like a snake. Then I draw a line from the start to the end. This is my resultant force, right? From the start to the end, pointing this way. So you can see over here for B, the resultant force is in the wrong direction. So B is not the answer, right? So the correct answer in this case is A. These two forces over here, connect them like a snake, then draw a line from the start to the end. This is the resultant force of A. Okay, so let me just show you another wrong answer. For C, I have these two forces and I connect them like a snake. This one should be my resultant of C, right? This one is completely wrong. Okay, so actually quite straightforward. Once you get the gist of it, it's quite straightforward to find the resultant force. Okay, now let's talk about drawing vector diagrams and solving structured questions using vector diagrams. Right, this one is a 4-mark question. It's a typical section B question where you have to use vector diagrams. Okay, so do read the question first, but I'm gonna go through the thought process to solve these kind of questions. So first of all, you want to be very clear on what's your goal, right? My goal over here is I have these two forces and I'm trying to find the resultant of these two forces. So I'm going to add these two forces together using the tip to tail method to find the resultant of these two forces. So my vector diagram should look something like this. I add this force, I add this force, and this one is my resultant force, right? I'm trying to find the resultant force. So it's always good to have a rough sketch of how your diagram should look like in the end. Now the second thing is to think about what's the scale that you're going to use for your drawing. So the scale is always going to be something cm represents something newtons, right? And generally the rule of thumb is you want to choose a scale that covers at least 50% of the question paper. So over here, I'm going to just choose my scale to be 1 cm to represent 1000 newtons, which means that when I draw my vector diagram, 1 cm of my drawing represents 1000 newtons, right? Which means that this force over here, I'm going to use 3 cm to draw this force, and this force over here, I'm going to use 4.5 cm to draw this force, right? And the important part for vector diagrams is that you must make sure that you actually draw it as 3 cm and actually draw it as 4.5. You want to actually stick to the scale that you use. And the importance of doing this is, I'm going to explain it in a bit, but yeah, you want to stick to the scale. You want to stick to the scale and you also want to stick to the angles. Meaning that if the question gives you 40 degrees like this, your drawing must also be 40 degrees to the horizontal, right? If the question gives you 30 degrees like this, you want to make sure that your drawing is also 30 degrees from the horizontal. You want to use the same length and the same angle as the question. And this is because it lets you draw an accurate vector diagram so that your answer in the end is accurate. Okay, so let's start drawing the vector diagram. I'm gonna start with drawing this one. So it's 3 cm at an angle of 40 degrees. So like this, right? This one is my 3000 newtons force. This angle over here is 40 degrees. Then I want to draw my this force, right? So 30 degrees below the horizontal and 4.5 cm. So it's gonna be something like this, right? So this one will be my 4500 newtons, making sure that it's also 30 degrees below the horizontal. So once you've drawn all the forces, you just want to find the resultant force, right? The resultant force is just connecting the start to the end. So this one over here is your resultant force. And here's the magic part, right? Because you have drawn everything according to the same angles, the magic is that when you measure the length of your resultant force, right? Over here, my resultant force is, roughly 6.2 cm. Now you can use the scale to find the magnitude of your resultant force. Because my resultant force is 6.2 cm, using my scale over here, then my resultant force must be 6.2 times 1000 equals to 6200 newtons. So that's the answer for this question. 6200 newtons, right? And the scale is 1 cm is to 1000 newtons, right? That's how you draw your vector diagrams. So let me just point out a few common mistakes. Common mistakes is that students will always reverse the direction of the arrows. So example, if the question gives you this way, right? The arrow in this way, sometimes the vector diagrams, it will end up like this, okay? But you always want to use the same directions that the question gives you. You don't want to change the directions of the arrows. That's the first thing. Second thing is you want to make sure that if it is 40 degrees from the horizontal, right, you don't want to end up your diagram is like this. You know, this one is 40 degrees from the vertical, which is actually 50 degrees from the horizontal. So these two are different, okay? So if it's 40 degrees from the horizontal, you make sure that your drawing is also 40 degrees from the horizontal. So yeah, that's just a brief run through on how to draw vector diagrams. Okay, in the next section, I'm gonna go into a different kind of question that they'll ask you. So now we talk about part 2 of vector diagrams. So imagine over here, if I have an object and I say that the object is not moving, what can you say about these forces if the object is not moving? If the object is not moving, it means that the resultant force is 0, right? Let's try to add these forces together using the tip to tail method. So what I'm going to do is I'm going to take my first force like this, take my second force and connect my third force like a snake. And what you realize is that the object, the vector diagram, starts and ends at the same place. So remember previously that if you want to find the resultant force, you want to connect them like a snake and then you draw a line from the start to the end, right? That's your resultant force. But what happens when the vector diagram, starts and ends at the same place? That's when the resultant force is 0. So the idea is that when the resultant force is 0 and you connect the forces like a snake, it will go back to the same place. So one very important thing I need you to understand is the difference between these two vector diagrams, right? Over here, that is not moving. There is no resultant force. So when you draw everything, it will go back to the same place. Now, over here in the diagram below, there is a resultant force, right? The forces are not balanced. These two forces, they will produce a resultant force. And so what you're going to do is you're going to connect the forces like a snake, then you draw a line from the start to the end, right? That's the resultant of these two forces. So you notice that these two arrows, they are in opposite directions because they mean completely different things. Over here in the first diagram, I'm simply connecting the forces like a snake, right? That's why the arrows is in this direction. But over here in the second diagram, it's like this, then draw a line from the start to the end to find the resultant. That's why the arrows is in this direction. So you gotta be very clear on the directions of your arrows, right? So now let's do some exercises. Let's try and solve this question. As usual, pause the video, try this question yourself first. Right, now over here we can see that the heavy ball is held in equilibrium. It means that it's not moving. So there are 3 different forces. There's the tension, let's call this, chain, let's call this cable, and let's call this weight. And the idea is that when you add the cable, when you add the chain, and when you add the weight, it must go back to the same place because the resultant force is 0, right? When you connect them like a snake, it must go back to the same place, right? So answer for this question will be A. This is the weight, this is the chain, and this is the cable. And as you can see, it will go back and start at the same place. B is wrong, not just because it doesn't go back to the same place, but also because the tension is in the wrong direction, right? Remember I said always don't change the directions of the arrows. If the arrow is pointing this way, if this one is the tension in the cable, don't go and reverse the tension like this, right? That will be wrong. Over here, if the tension in the chain is this way, don't go and change it until like this, right? Always use the same directions as what the question gives you, right? So let's do one more exercise before we end off with a structured question for dynamics. So over here, which of the following shows 0 resultant force? So the answer will be B, because when you connect this one and you connect this one and you connect it like a snake, it will start and end at the same place. So there's 0 resultant force. So some students might ask, why is A wrong? Because A, you are connecting F1, you are connecting F2, then you're drawing a line from the start to the end, right? A is saying that F3 is pointing this way. So F3 is actually the resultant of F1 and F2. This one is F1 plus F2 plus F3 added together. But in this case, F3 equals to F1 plus F2, right? F3 is the resultant of F1 and F2. But we want to find, in this question, what's the resultant when all of them plus together and there's 0 resultant force, right? So answer for this question is B. Okay, so now that we're used to this, let's try to end off with a structured question on vector diagrams for these kind of 0 resultant force questions, right? So this one is a vector diagram question. As usual, feel free to pause the video and try this question yourself first. So first thing I want you to do is always draw all the forces acting on the kite. So there's the weight acting on the kite, there is the tension pulling the kite this way, and because we know that the kite is held in position, position means in this case the resultant force is 0, right? First I need to see the difference with the last question. In the last question, the resultant force is not 0, right? There is a resultant force, which is what we're trying to find. But in this question, the kite is held in position means that there is no resultant force. So we can kind of guess that the wind is blowing the kite somewhere in this direction, right? I don't know the exact angle, but I know that the wind is blowing the kite this way. And the plan for this question is that when I add my weight, when I add my tension, and I add my wind, what's going to happen is going to start and end at the same place because there is 0 resultant force. Okay, so this is my rough sketch of my plan for this question. So as usual, let's start with thinking of the scale. Over here, I'm gonna just use a scale of, the weight is 5 newtons and tension is 40 newtons. Okay, let's just use a scale of 1 cm is to 5 newtons. Right, so my weight will be 1 cm and my tension will be 8 cm. So now I'll start with drawing the weight. The weight is 1 cm downwards. Then I'm gonna draw my tension. Now you gotta be very clear about the angles that you draw. We know that our tension is 8 cm long and it's also 20 degrees from the horizontal. Means that when we draw our line, we must make sure that it's 20 degrees from the horizontal like this. So 8 cm, and we gotta make sure that this angle over here is 20 degrees from the horizontal, right? Always draw the same angle as the diagram. So this one will be your tension, and because we know the resultant force is 0, when you add the wind, it must go back all the way to the start. So this one will be the force of the wind, right? And because we have drawn everything according to scale, what we can do is we can take our ruler and measure the length of the drawing for the wind is roughly 8.3 cm. So this wind over here is 8.3 cm. Okay, because the wind is 8.3 cm, the force of the wind must be 8.3 times 5 equals to 41.5 newtons, right? And that's how we use vector diagrams to sketch out the question. As for the direction of the force due to the wind, this one basically, you want to measure this angle over here. So the angle from the horizontal like this, right? So this angle is roughly 27 degrees. So I'm going to say that the direction of the wind, because we are going anti-clockwise over here, right? So the direction of the force of the wind is 27 degrees anti-clockwise from the horizontal, right? Because over here is the horizontal and we are going 27 degrees anti-clockwise. Okay, so that's pretty much it for vector diagrams. And yeah, really, once you understand the logic that, you're adding everything like this chapter becomes quite easy to solve. Alright, so that's the full course on dynamics, and I really hope this video helps you, especially if you are in Sec 4 or even if you're in Sec 3, right? Just preparing for your first chapter of Sec 3. Feel free to share with your friends if they need help for physics as well. And also, if you want to get tutored by me for physics and join my regular classes, feel free to just WhatsApp the number around the screen. And if you join, I look forward to seeing you in class. See you in the next video.